this particular webinar, it's part of the Decoding DevOps Machine Learning by DevOps Artisan. I'm pretty sure you can find more information on the internet, and also you can ask questions regarding this particular webinar and the work we will interactively do in this seminar. Following links with the email address I will show you in a few seconds. So this is me. I'm the AI guy. So basically, I also teach data science with deep learning at the Computer Science University Polytechnica in the Faculty of Computers and Information Systems. I work with a very nice team of AI experts and researchers and engineers. And one of my colleagues is actually assisting me in this webinar. Hi, Alex. So without going into too many details about me and what I did in the past, let's go straight to our problem and our short journey for today. Hopefully that our today's webinar will give you a taste of the courses and interactive sessions that you can do together with DevOps Artisan in future. Of course, you will be able to go back to this presentation. Like I said, there it is, the email address I was promising you. And you can also see the entire recording of the webinar. Okay, so without more introduction, I will tell you a few words regarding exactly what we are trying to do today. We are trying to enter the, let's say, have a taste of what it means to work in data science, to work with machine learning, to work with both shallow learning and deep learning, deep representational learning. We're gonna see how we can do things simple in Python. We're gonna use IPython notebooks. We're gonna use Tensorflow. We're gonna use PyTorch. We're gonna use we are gonna even use simple libraries from Python, such as numpy, in order to generate the most basic machine learning models that are available right now and that can be expressed through simple mathematical equations, linear equations in particular. But first of all, let's answer a quick question. What is data science and what is machine learning and how they are connected? First of all, data science, it's basically science, like the name suggests, that basically its main focus is the study of natural phenomena and methods and let's say methodologies that humans can use in order to better understand, infer the results of natural phenomena, and also predict potential outcomes of natural processes through the use of mathematically and self-learning mechanisms. So not by using classical computer algorithms, by using machine learning, self-learning methods that where algorithms are not created by humans, but the algorithms are actually created by the machine, by the computer. So I tried to start with the simple, intuitive explanation of data science and go straight to the idea of machine learning and what machine learning means. So again, machine learning means having smart algorithms, artificial intelligence, let's say, not based on algorithms, not based on human design algorithms, but based on algorithms that are self-created by other algorithms, by computers. Okay, why data science and why now? What is different right now than, let's say, 20 years ago or 30 years ago? Because let's think about it. 30 years ago, we had very powerful computers for that age. 20 years ago, it was the same. So it wasn't like, let's say, 60 years ago, where there were no actual real personal computers at all. 30 years ago, we had personal and powerful computers, as well as 20 years ago. So two different things. I will start with the less important one, which is the powerful evolution of the gaming industry, and in particular of the computer graphical unit cards, GPUs, that make available beautiful games to everyone, but also are able to make millions of computations, of numerical computations in parallel. Those vastly expanding the capabilities of numerical computation and making it available for individual scientists, not only for big research complexes. Okay, so this was, like I said, it wasn't the main driving force behind data science and behind machine learning and deep learning in particular, but the main driving force is the availability of data. And this will be one of the first focuses, the first subject of our webinar. Probably you already hear everywhere that data is the new electricity, or AI is the new electricity. And let's say that data is the fuel of this new electricity. If, let's say, 30 years ago, we could find a few tens of data sets, of collections of observations of data or real life phenomena, now we can find millions of such data sets. If 20 years ago or even 15 years ago, those data sets were containing, let's say, between hundreds of observations, hundreds of records, of database records, up to millions of records. Today, databases are containing billions of records. So basically, now is the right moment for machine learning, for deep learning, because we have the compute capability, we have the mathematical models. Actually, we had the mathematical models for a long time, but we couldn't try them out, let's say, correctly, and the science couldn't really advance in the direction of data science and deep learning as we know it right now, because the data wasn't enough to train the models. And this basically concludes our presentation, stating that intuitively those algorithms that I was talking about are not simply made out of thin air, but instead they are made and they are learned by other genetic algorithms, let's say, through understanding of the data. So basically, let's say that intuitively we can see machine learning as a child that doesn't know anything. It's tabula rasa, and let's say somehow it's able to read information on a particular topic, and the more information it reads on that particular topic, the better it understands that topic, that process, that natural phenomena, or whatever that it is described in those particular records. So this is a very, very superficial and probably a bit unrealistic comparison, because humans are a lot smarter than machine learning algorithms. But I think it's an intuitive understanding of how machine learning works in general. Okay, I'm gonna skip this presentation a little bit further, as we are trying in this webinar to compress the whole information, let's say in tens of hours of courses, in just 100 minutes. So I was saying that data is the main driver of today data science and today deep learning. And for this particular webinar, we decided to use a data set that was created by a group of engineers and researchers from United States, and they made this data set available. So basically what they did was collecting from different cars, sailors, and I don't know, online websites, for example, or public announcement for car sales, for used cars, of course. They collected about 400,000 different cars, 400,000 different announcements, which is not much in today, let's say, ranges of data quantity that today data sets are, let's say, are available for everyone. But it's a lot more than they used to be, let's say, 15 years ago. Just to give you a rough example, a data set for, let's say, a different topic for real estate that was collecting announcements for house prices, and was collected, how this data set was collected by a company somewhere on the west coast in the United States, I think, about 20 and something years ago. And at that moment, it was considered a very important data set for determining and for understanding how the price of a property is correlated with all its assets. So basically, it was used for creating electronic property asset software. So basically, you would go and say, okay, I have an apartment in this address with this at this floor, and it has this furniture and whatever and so on. You complete the form, and the system was giving you an approximation of a real market value for that apartment. So like a human appraisal, a human appraisal transformed into an electronic virtual property appraisal. So that particular data set was very big for that moment. It was a few thousand records. This data set where we are talking right now has a few hundreds of thousands of records. So we already downloaded the data set. We will make everything available to you. So all the source code and all the entire seminar structure, which is structured in 4 different notebooks. We're going to use Jupyter Notebook, which is a very good technology for working in general with Python, with data science, and we strongly recommend it especially in the learning process, both for academia and for engineering purposes. So we're gonna have 4 different notebooks. We're gonna have access to the data sets, and also you're gonna be able to have a sneak peek in the way we actually process those data sets and prepare them for you. So let's go straight and start our journey. I think we are a little bit maybe ahead of time, which is good, not sure. And probably we will stick more for dataset understanding. So we're gonna use pandas, we're gonna use numpy, and we're gonna use again, I'm not going into deep details of why we're going to use pandas. This is a package for data processing, simple data processing, not, let's say, not production grade data processing, but more like experimental data processing in Python. It's a very widely known in data science community. And numpy, which is a numerical Python library that can help you do a lot of linear algebra. I'm not sure a lot of you love linear algebra, but you have to love it if you want to do data science. Okay, or at least you have to make friends with linear algebra, right? So we're gonna load the data, and now we're gonna see how the data looks like. So this is how the data looks. We have the the first five records in the data set. Let's ask for more. Let's ask for 25 records. Okay. So basically, we have a column with car prices, which is, I'm pretty sure it's in US dollars. We have the region where the announcement was posted. We have the production year of the car. I think we have a very wide range. We're gonna see that. We're gonna have a look at that. The manufacturer of the car, the model of the car, the condition of the car, the cylinders, the fuel, the mileage of the car, basically what is written on the mileage inside the car, which everybody knows can be different from the actual number of kilometers, which is something, you know, maybe the odometer was flipped and restarted from zero, I don't know, for whatever human or not human reason. Okay, the transmission, manual, automatic, the type of drive, it's rear drive, it's forward drive, it's four-wheel drive, the type, mid-size, the type of the car, and the paint color. Okay, so this is the data set. Like I said, it has a lot of records. Let's see how many records it has. So we're gonna see the shape of the data. It's this one is 90,496 by 14 different columns. That is because we already did some processing for you, like I said. So we decreased the number of records from 400,000 records to only 90,000 records. And I'm gonna ask my colleague and my co-instructor Alex, and he's doing some extra work on telling me the time. I think it's good enough. I think I have enough clocks around me. Just yell when I'm over my allocated budget for this particular subject.
Actually, you only have 2 more minutes for
okay.
this section.
Okay, and then we have to go straight into the shallow, into the basic machine learning, right?
Yeah. Yes.
Okay,
yes.
Perfect. So this is the data, and let's have a quick look at how some of the particular information and data looks like. Let's say, what is the range of the prices? Okay, let's say the range of the prices is this one. So basically, we have a maximum price of 6.9 at the power of multiplied by 10 at the power of 7. So that is, I think, a lot. Let's try and round things up. Okay, so price. Okay, as type, I think it works. Okay, int dot describe. Okay, I think it didn't change much. Anyway, this is the I was trying to show you the prices into a more non-scientific way to view them, but I think you can do that by yourself on your own computer when you download the seminar. Okay, so let's see another one. Let's see the year. Okay, and for the year, although it looks like a number, actually it's not a number, it's more like a label. So by number I mean quantities, things, values that can be represented as a continuous value, not a discrete value, and years are discrete values, not continuous values. So you cannot say that 2020 it's bigger than 2019 because it's not bigger, it's just another year. And for example, in terms of economy, 2020 for certain is a lot smaller than 2019. Okay, so we're gonna have year, and we're gonna need the system to show us what years we have. So we have quite a few. We have also from 1930, very nice. Let's see what car we have from 1930. This is interesting. Okay, so let's have a look at the car that year is in. Let's say all these here. Okay, we can consider all these as all these. Okay. Okay, year is less than 1940. Okay, let's see just a few, not many. Okay, very interesting because the first one is a car that's it's $17,000 US from the Space Coast. I know it's East Coast, West Coast, by Space Coast. Maybe I don't know enough US geography, so I apologize. Okay, so it's a Chevy from 1939. Okay, so we have another car which I think has a very large number of kilometers. With a Buick from 1925. A Mercedes from 1921, and so on. So we have quite a few selection of old cars, and they're not very expensive as compared to the maximum. So again, the maximum price in our data set is, again, it's a very crazy price. It's actually 69 million US dollars, and that's quite a few. Okay, but who knows? Let's see, what car is this? It's a very expensive car. Let's see what car is. Price, it's bigger than, let's say, 1 million euros, $1 million, sorry. Okay, and just a few entries. So we have a Cadillac from 2016. Okay, and this with Cadillac, it's $1.9 million. Okay, this is strange. Doesn't make much sense if you ask me. As well as a Chevy from 2012. Maybe this silver here is actually silver. I don't know. It doesn't really matter. Let's move on. This is the data set. What we are trying to achieve now. So what is the problem? What we are looking at all this information. So right now I'm gonna go back a little bit to the initial idea of data science. What we are trying to achieve through data science. Let's say that you are making a website or a service publishable for a web service. If I were in a class with you, I'll probably ask to raise for all those who are software engineers to raise their hands, so I can see how many of you could actually do such a product. So let's say that you have the task of making a website that receives customers, and the customer pay in order to have a car appraisal system. So basically you go into the website and you give everything you know about your car, and the system should tell you how much could you get for that car, like a a real human appraisal. So what is an appraisal? And looks at your property, you look at your goods and say, okay, you can sell those goods, your very nice shiny shoes or very nice property or very good looking car for this much amount of money. So let's say you want to make this electronic service, a website that does this particular task. Okay, so basically what we are trying to achieve in this experiment, we are trying to construct a system that is able to predict the actual price of the car based on all this information. So basically our system should be able and should be able to create a self-learned algorithm that it's able, when you input this information, for example, this region, this year, Cadillac, whatever information this car has, it's able to tell the price, to say, okay, I think this car is worth, let's say, $50,000 or $5,000 or $27,000. Okay, so this is our subject. Construct a car appraisal, automatic car appraisal system. So for this, what we are trying to do, we're trying to build a mathematical model through several different approaches that will be covered in different classes, in different stages of the whole course that maybe you will be able to attend, through different methods, through basic methods, through advanced methods, through things that could be transformed into a real production grade system. Okay, so like I said, this is the data set. What is important at this stage, we are going to build a shallow model. We are going to build a so-called classical machine learning model that will try to infer the price of the car based on these properties. And the first thing that you can observe here is that all the information beside the actual price and beside the year, all this information, and of course the mileage, apologies, beside those three, all this information it's only human readable. So basically a mathematical algorithm, a mathematical method cannot compute what it means to be Cadillac or ATS or automatic or real wheel drive. So what a data scientist should do in this experiment, first construct a mathematically interpretable data set out of this particular one. So the most basic approach would be to assign, let's say with software engineering methods, indexes for all the unique values, such as here. Okay, so we have how many years, let's say year and unique. We have 94 years in total. So basically we can assign different values, but that's not the right way to do it, because if we assign numbers from 1 to 94, we arrive in the same position where we can where the model assumes wrongly that there is a year, let's say the year 93, that it's bigger than year 92, which is bad, it's wrong, it's not anchored in the real life. So the system must know that the years are not bigger from one another, they are just different years. So the method that we are going to use for this particular subject is to ask the system, to ask the package that we are using, in particular pandas, to generate binary features, binary variable for all those categorical values that we see here. So basically, let's say we have condition. Let's look at condition. Condition. Okay. Okay. So condition is excellent, good, like new, fair, new, salvage. So from the best, which is new, then going to excellent, good, like new, okay, new, sorry, like new, excellent, good, fair, up to the worst, which is salvage. So for this 1, 2, 3, 4, 5, 6 different categories, we can code them with binary variables that would tell the mathematical model that, okay, this particular record, let's say this one here, it's 0 for excellent, 0 for good, it's 1 for like new, it's 0 for fair, 0 for new, 0 for salvage. So basically, using a numerical binary vector, we can tell the system that our record, our observation, like we call it in data science, belongs to a particular class. What we are going to do right now, we are going to clean a little bit the data, meaning that we're gonna straightly drop, and this is not the right way to do it, but we are going to do it here just for demonstration purposes in this particular webinar. Is not the right way to do it in data science in general. So what we are going to do, we're gonna see for each of those features how many different values they actually have. So for price, it doesn't really matter because it's not a categorical feature. What it matters also for the mileage, it doesn't really matter. What it really matters is this model here. So basically, for model, we have 10,000 different models. That would mean we need a vector with 10,000 binary values. In this particular case, in shallow machine learning, you have no other option but to do this, and this is the bad way to do it. The right way to do it would be to use smart things like transforming this data set from the binary form that would have over 10,000 features, over 10,000 different columns, starting from this only 13 plus 1 columns, and to apply a mathematical model that compresses this information into a more interpretable form. And that would mean using something like principal components, independent components analysis. Okay. Again, this is something that we would probably and most certainly do during the courses, but not right now. So we're gonna just drop the model. Okay. Okay. So now the new status of the data set is this one. So we still have a few hundreds of features, but I think it's good enough. What we are going to do right now, we are going to have a look again at the columns. Right now, I'm gonna move a little bit faster from now on. My colleague Alex is probably
6-7 minutes left for this section.
Okay, thank you. Okay, so what we are going to do, we are going to consider a variable, a vector y, as the actual, let's say, target of our experiment. What we are trying to achieve, what our algorithm is trying to learn, prices based on different features. So we're gonna take y as the year, okay, and we are going to also pop the year. So we could just do something like pop it year, okay. So we got rid of the price, and we'll still left with all the others. Okay, we're gonna copy them. Okay, so these are the columns. What we are, why would our target right now is to transform, let's say, the region or the year or the manufacturer from these not unusable forms like, okay, df dot region, too many, let's say dot manufacturer. Okay, a lot of them, 42, from this format to a binary format. And we are going to do that by saying, okay, I have these columns, I have, and actually I want to write which are categorical columns, and I'm going to delete the odometer, which is not a categorical, it's a continuous value, it's just the mileage. And the price was already taken out. Let's have a look again. I think we are good, nothing else besides this. Let's have a look again at the data. So we have the price, which is continuous, region, categorical, 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 continuous, and everything else is categorical. Perfect. Okay. So this is how it looks like. And now we are going to have a different data set called df sparse, because you have sparse data. And sparse like in mathematical sparse. Okay, pandas get dummies of df with the columns, categorical columns. So basically it's asking our package, our data science library to help us transform all these columns, this one and this one and this one and this one, from this format to a binary format. And let's see how it does that. Okay, do we have an error? Here is not an index. Okay, I think I left something somewhere. Okay, first of all, I made a mistake. So I popped year instead of price. So it's okay to make mistakes in data science. What we have to do, unfortunately, we have to reload the data. That's not a big issue. It goes pretty fast. Okay, okay, again, all the experiments we did, all the exploration. This is extremely fast, like I said, and this should be done thoroughly, and we should see distributions, distribution plots. We should better understand how the data is actually looking behind. Okay, we pop the model, and we have these columns. We pop the price. We have these categorical columns, we have this manufacturer information, and we obtain the sparse matrix, and it's obtained. And now let's have a look how let's see how the actual this matrix sparse looks. Sparse dot shape. So it has again 90,496 records, but this time has 593 columns, a lot of columns. Let's have a look at the first 20 columns, let's say. df.ilog, the first 10 observations, and the first, let's say, 15 columns. Okay. Okay, but that's not the right one. This is the right one, the processed one. Sorry for that. Okay, so this is how it looked like. The other method is not changed. And we have, for example, the first car, it's region SF Bay Area, Albion, Akron, Kent Albany, Albuquerque, sorry, okay, Amarillo, and so on. So basically, in this particular line, all this region are zeroed because the actual region is Space, no, not Space Coast, sorry, it's Mojave County. Okay, so somewhere around here it's Mojave Country. I'm not sure where, but it's somewhere. And for that particular column, the number here is 1, not 0. Maybe you have luck with another one, Maine, let's say. Okay, Maine is the second one. Maybe you have Maine around here. I don't see any Maine. Again, I'm using only the first 15 columns out of those 593 to show you what happened with the data. Okay, So now we are going to take data as a matrix. Okay, and this X has the shape 90,496 lines by 593 columns. Is just a matrix. Okay, if we I'm going to plot it, it will not show very nicely like this database data frame. Okay, and what we are trying to achieve right now is to build a regression model that will be able to compute the price of the car based on those features. But first of all, let's do something in advance. So we're going to build a model, and this model, in order to be tested, we have to hide away some data out of these 90,496 records. We have to hide a few cars. Let's say to hide, I don't know, 10 cars, 20 cars, I don't know, maybe a percentage would be better. And we have to hide these cars from the model, and then use those hidden cars and ask the model to tell us the prices, and then we can compare the prices in the hidden for the hidden cars with the predicted prices, with the inferred prices for that particular car. Okay, so in a correct data science experiment, we have to sample those hidden cars. Sampling means find a way to randomly and probably uniformly pick cars out of the data set and keep them hidden from the model. This time we're going to do it the worst way, and we're going to pick the last 100 cars and not show them to the model. So let's say the X train is not train, it's like in train, it's like in train, like in training. Okay, so it's X, all the observation up until 100, and we have Y train, all the observation in Y up to 100, and we have Y task. Again, don't do this at home. This is not the right way. The right way is sampling based on percentages, right? And that's another discussion, and that's another topic in the data science. It's actually a research topic, and we're gonna do it in our seminars, in our classes, if you will attend to them, of course. 100 up to the end, Y test, it's Y 100 up to the end. And I think this is it. So let's have a look what happened here. Okay, X-train, it's, okay, I made a mistake. It's up to minus 100, sorry, my bad, my mistake. So up to the last minus 100%. So you take everything minus the last 100. Okay, like I said, it's okay to make mistakes. So in X-train, we have 90,396 observation, and of course, by 593 features. And in X-test, of course, we will have 100 by the same number of features. So now we build the data, and we want to train the model, and we want to test the model, and we want to see that our predictions are similar to this particular data, to Y test. Okay. So right now I'm going to show you the most straightforward and simple regression model that there is out there, and that is based on a simple mathematical linear equation, linear algebra equation, which is called normal equation. It's a closed form of, let's say, optimization. It's not actually optimization, but it's determining the parameters of the model. So the model is just a matrix. It's not a matrix, sorry. It's a simple vector. It's a simple vector that explains us what is the importance of each individual feature out of those 593 different features in relation to our subject, which is the price determined, hopefully, by those features of those individual cars. So the equation basically it's y, it's x, sorry, it's x transpose. I'm gonna write it like this, multiplied with dot product. So it's a linear algebra matrix multiplication. It's not Hadamard product, so it's not element-wise product. It's matrix multiplication product, and this everything it's inverse. So it's power -1. This again is multiplied by x transpose, and this in turn everything it's multiplied, matrix multiplied with the vector y. So this is the equation. Let's write it in with numpy very nicely. So linear algebra, we're gonna use direct inverse, although sometimes this matrix could not be inverted, but we're gonna use a trick. So we are gonna use regularization in this particular normal equation by adding a scaled identity matrix. So it's x train dot transpose dot multiplied by x train, everything added with let's say the scaling of the identity matrix. Let's say it's 1.5, and this is another subject that we will discuss. Everything will be subjects that we will discuss in our classes. Okay, and now we create an identity matrix that has, of course, the shape of the number of features, which is the second number in the shape of the training matrix. Everything is dot multiplied with x train transpose, and everything, of course, is finally multiplied with y. If you put this equation on the paper, you can understand it intuitively very easily with simple basic mathematical understanding. You don't even need linear algebra to understand this normal equation. You need linear algebra to prove it, of course, but in order to understand it, it's very easy. Basically, it's a simple, it's a very simple first-degree equation. Okay, so
just 1 second. I think the last dot should be with y train.
Okay, y train. I apologize. It already gave an error, and now I think it should work. Okay. So we have theta, and theta is, like I said, it's 593 features. And now we can test the model by simply saying my predictions for those 100 cars, let's say, okay, equals with the data for those cars multiplied by theta, by those coefficients, and that is all. So these are my predictions. Let's see how we fare, how we compare those two information. Right now, we're gonna see it visually and measure it with the most simple way. So basically, the mean average error. We could also use mean squared error, to have a little bit of eye candiness. We're gonna use a pandas data frame in order to show us the comparison. Okay, sorry, this way. And now we have the dictionary, and now we write the predictions. Okay, which is y pred 100 cars, and the reality, which is y test, right? So this is it. Okay, so it's 100 by 2 columns. We can see here that sometimes it's okay, like here it's 1,000, 8,000 versus 11,000, the prediction. Sometimes it's pretty good. The reality is 14,000, and the prediction is amazingly $14,643. Some other times the prediction is not that good. For example, this $43,000, the prediction was $26,000. Maybe this is the right price. We don't know. For this one, also the prediction is pretty good. For the $3,200 cars, the system predicted 2,700. For this one, 12,000, 13,000 almost, it predicted almost 12,000. So the predictions are pretty much good in a lot of cases. This one is okay, this one is okay. This one is not okay, but it's, you know, close to this price range. 31,000 is not, let's say 10,000 or something like that. So the prediction are looking good. So basically we did our first AI model. And let's see how this actually translates in actual performance. So we are just going to subtract the prediction out of reality and take the absolute values and take the average and see how this looks like. So we're gonna have MAA, mean average error, equals npy.abs, absolute value out of y pred 100 cars minus y test. Alex, tell me if I'm going okay with the time. Okay.
We're off by 10 minutes.
Okay. Okay. So okay, sorry, it wasn't me, it was MA.
Yeah, but it's important, and I will try to be a little bit shorter in my section. Okay.
Okay. So basically, the error is $5,000. So the average error of evaluation those car is $5,000, which is pretty good, I think, if you ask me. It means that the model has a very, very good potential of giving you a right price for that particular set of features in your car. And we're gonna take this example, and then we're gonna implement more advanced models with different frameworks and with different approaches. But until we played with those, we're gonna show you something different and something that you might not like a lot, but it's a preview of our courses, and it's very important for data science, and that is understanding symbolic tensorial operations and understanding how we can use GPUs, how we can use advanced compute capabilities of our everyday computers in order to generate powerful mathematical models, powerful machine learning models, and of course powerful deep learning models. So I'm gonna start with this notebook here. I'm gonna save it so we can push it to the GitHub and also send it to you with the other presentations. Okay, and we are going to, how many minutes do we have in for the tensorial computation part, Alex?
There are 20 minutes.
No, how many minutes do we still have?
Do we still have 9?
9, it's good. Even if it's bad, it's pretty good, right? So, okay, so we are going to use one of the first frameworks and probably the most widely used deep learning framework in the world right now, which is called Tensorflow. And Tensorflow was developed and is still developed and used internally by all the AI projects within Google. So if you're using Google Search, if you're using Google Translate, if you're using whatever product from Google, which is more than certainly has artificial intelligence behind, analytics, whatever, you can imagine that behind scenes, there is a library called TensorFlow that makes millions of computations in order to give you a most likely answer that you would like, okay, or you would need. Okay, so like I said, it's called TensorFlow, and just a second. Okay, so TensorFlow, it's a library that basically aims at helping scientists and machine learning engineers describe their models and describe their mathematical models in such a way that they can be easily computed, easily and massively parallel computed on GPUs architectures or on distributed GPU architectures. And what I'm going to do right now, I'm going to repeat the same experiment that we did with NumPy, with the basic classical numeric algebra and numeric library of Python. I'm going to do the same thing with TensorFlow. Okay, so we loaded TensorFlow. We have to load the data. Maybe I should have used the same notebook, but now it's too late. Let's just import those here. Is that cheating? It's very natural. Okay, and let's add the data definition. This is, you will be able to find the data in this subfolder of the seminar, so don't worry about that. You can have a look at it by yourself. Okay, so we read the data. Now we have to straightly construct the final data set. So first we had to pop the model column, and then we have to pop the price and put it into a variable, and then we have to generate the dummies. That is the binary features for each categorical feature. But first we need to have the columns. Okay, we can put it here with no column. I think that's good enough. Okay, and now we have everything. Let's check one. Also, there is something that we say in our team. I asked my colleagues a long time ago to make a t-shirt for me that would say very big sanity check. So in our field, in data science, in machine learning, deep learning, everywhere, the most important rule is that always triple check, quadruple check. There is no, I cannot find my words to tell you how important and how paramount is the sanity checks. Always sanity check your experiment. Always sanity check your data. Always sanity check what you're doing. Verify that everything is as it should be. Okay, so the DF sparse is as we expected it would be. Now we slice data so we can update the training, and now we have the same experiment, and we could use NumPy, of course, and compute the data. However, why we would like to imagine that this data, let's say it's 1,000 times bigger than ours, and if we are using NumPy, the processor which only has, I don't know, 2 cores or 5 core or 6 core or 4 cores or 8 cores or maybe 12 cores, you have a very nice computer, but it's not enough to compute millions and millions of multiplications and additions. However, your graphical card, and you might have, I don't know, even the cheapest laptop graphical card has at least 300, 400 different numerical cores. And those cores are able to numerically compute basically the same amount of data as the GPU in a matrix multiplications hundreds of times, maybe faster, or tens of times faster. No matter what, it's a lot of times faster than the classical CPU. So basically, what I'm going to show you, I'm going to show the same operations, but I'm going to do them inside the TensorFlow. Okay, the framework. Just a second. Alex, maybe you can help me with the method for inversing a matrix in TensorFlow, so we can finalize this. So
yeah, just a second.
okay.
TF linalg
just a second. When I'm gonna need it, right now I'm gonna set up the tensors. Okay.
Okay.
Okay. So we're gonna set up the symbolical tensors. Okay. TF y train equals TF constant. Y train TF x test equals TF constant. The x test. We didn't transform into a tensor the y test because it's not needed. We're gonna need it just when the computation finishes, and we're gonna compare it like we did in the previous one, in the previous part, and this will be straightforward. How many minutes, Alex, please?
Off by 1 minute.
Off by 1 minute. Perfect. Okay, then I'm gonna finish in 2 minutes.
Yeah.
Okay. So right now we are loading all this data, all this information basically are loaded into my local GPU card. Okay, and it didn't like the fact that I missed a T, and it doesn't like that I missed a capital X. Okay, now we're good. So if we look right now at X train, it will say that it's not a classical array, however, it's a tensor. And it can also show the information of this tensor. And I think we can also see the actual device. So basically, this particular operations did not move the data into the CPU. I should have asked TensorFlow to explicitly create this information in GPU. However, in the newest version of TensorFlow, and from now on, it will be like this. All the constants are by default created on the CPU and cannot be created on the GPU. If we want to create, let's say, constant on the GPU, we have to declare variables, and those variables can be uploaded into the GPU. So no matter what, if we are using constant, it will not show here GPU column 0. It will show, or column 1 if you're using, let's say, the second GPU of your computer. It shows CPU. So basically, it tells us that I have this data. Okay, def x train. I have this data, and this data is located in this particular location. It could have been on a different computer, because the whole purpose of this framework is to compute, to calculate, to do a lot of linear algebra and optimization, and also other high-end functions such as computing convolutions, deconstructing recurrent neural network, helping you construct those beautiful GPT or transformer models that make so very nice words out of thin air, on distributed computers, on distributed GPUs. Okay, so right now let's make the theta straight. So you said it's tf.linalg, right?
Yes.
Dot
inf.
Okay, so it's tf.xtrain it's tf.transpose .xtrain. Okay, and now we have a tf xtrain, and we have here tf.matmol, I think, right? Maybe you can check. You don't have to remember everything by heart. You have, for that you have huge encyclopedias. You have to understand the mathematical. You have to understand basic. Data scientist doesn't have to know all the mnemonics. Tomorrow, maybe you will switch another framework. You don't have to remember everything by heart. You have to understand how it works, and you have to know exactly what you have to do. And then you can use any kind of framework, any kind of keywords, any kind of methods, whatever. So Alex, is it matmol or it's different? I think it's matmol. Can you check, please?
Yeah.
Okay, so it's okay. Let's say this is A. Let's say if it works. No, it doesn't. So it failed because it doesn't like something in our information. It's transpose. Okay, let's have a look at tf.mat. It's transpose A false, transpose B false, and it's right. This is the operation. Okay, but we transposed A X train, so it should have worked. A shape is 500 by 90,000. B shape is 90,000. Okay, I think it was something else. It wants that we say transpose B. Okay, let's check the exact definition of mathmol. Again, I cannot emphasize more what we are doing right now. We are showing you how the reasoning behind has to be done, right? Okay, so basically we don't need to transpose it. It seems it says that it's better to just use transpose A. Transpose A equals true, and that is didn't like. I forgot one. Okay. So basically it says, okay, multiply those two matrices. However, please first transpose the first matrix. And this can be done, I don't know, maybe on another computer or on a GPU or something like that. Okay. And it generated a tensor called TFA, which is on the device. Okay. And it works quite a bit. Let's have a look what happens behind. Okay, so this is the log of the operations that are behind. Okay, it's a little bit unhappy. It didn't manage to generate, to construct the dynamic libraries, the dynamic link libraries for our okay. So it says CPU to GPU mem copy failed. Okay, probably it's just a problem of let's say too small GPU memory. Okay, so we data scientist has to know to interpret what the actual logs are generated by the framework. Doesn't matter if it's own framework, his or she's framework, or it's a Tensorflow framework log, or it's a PyTorch framework log. Yeah. Okay. So basically, we have a problem with the Tensorflow. It couldn't copy the matrices from the CPU memory to the GPU memory, and because of that, it actually died. It actually and basically failed to construct this computation. So what we're going to do right now, we're going to save, and we are going to restart the kernel and restart the GPU. Okay. Okay. We're going to restart the Jupyter notebook. So the Jupyter notebook is right now, it's restarting. Okay. We're gonna go into the tensors notebook. Okay, again, it's the TensorFlow is loading. We can see here that it will try to load the libraries. It will try to connect to the GPU. I'm using NVIDIA 1070 GPU card. It's a laptop based. It's a max card, so basically it's a bottleneck. It's a efficient card, let's say, for laptops, and has 8 GB of memory. Okay, I think the TensorFlow is loaded. We can actually see what version of TensorFlow we are using here. tf.version. Okay, so we are importing pandas. Again, we are passing through all the tensor are again on the CPU, and we are retrying the algorithm. Let's have a look at what happened behind the scene. So it actually computed very fast and very nicely. Okay, and if we look at the TFA device, this time it's GPU, it's not CPU. So basically what actually happened is the system took those this tensor X-train, it copied in the GPU memory this tensor, it transposed this tensor, multiplied it, and then inversed the whole result. And this happened almost instantly, as you could see, in the using the GPU we are using. And here in the log, you can actually see that this actually happened. It doesn't say that it copied the memory, but it says that it created the device and successfully opened the CUDA processing libraries and so on. But you cannot see exactly that, okay, I copied memory and so on. There are so many operations that if you log all them, you will not be able to understand anything. But those the important ones are, and of course the errors are shown. And of course, now the next step will be to compute the TFB, let's say, or even better, the final TF theta, which is the TFA. It's a tf.mathmul, right, of TFA dot TF X-train, right? Transposing the TF X-train, right? The transpose B, and everything should be multiplied with y. Alex, correct me if I'm wrong, please. Okay.
Seems okay.
Okay, TFY train, and this is it. No other operation. And this is it. Okay, transpose B is not defined. Transpose B, of course, because it's true, it's a parameter of the function. It doesn't like something, cannot multiply. Okay, as input 0 base, we said to be a double tensor, but in 32. Okay, so it doesn't like the operation that we did with the Y train, because probably TF Y train is not a float exactly, it's an integer tensor. So what we can do quickly, I'm gonna leave this error here because you have to remember this kind of error. It's going to happen when you do real data science. Okay, so I'm gonna leave it here, and I'm gonna leave to you the rest of the steps. I'm just going to show you that we should have done tf.constant.xtrain the type equals float 32. Okay, sorry, it's not the Y train. Good to give an error. And now if we again compute this, it shouldn't give an error if everything is okay. It gave an error. It doesn't like because was expected with double sense, but it's float. Okay. And that is because we decided that this one is float 32. We should put it double precision. And now it should finally work, but it still doesn't work. In one is not a matrix, it has shape 93,000. Okay, so basically what we should do, this should be reshaped in the form of a correct matrix. I'm going to leave this error because this is another important error that you have to remember. So TF Y train, then this is the last piece of code. The rest of code I'm going to leave either to you or for the classes. Y train equals TF dot, I think it's reshape, right, Alex? Not sure, let me check. Reshape, okay, exactly this one. So it's TF Y train TF reshape of TF train dot shape. It's the shape is none by one. Okay, meaning it's whatever you have there by one. Okay, it's Y train. Okay, not an error. Okay, supported none. Okay, doesn't like none. So maybe it works with -1. It works. So the shape of TFY train, we're gonna show it entirely. It's 90,396 by 1. So if we copy paste again the whole story, it's flow 34, everything is in place and it should work, and it did work. Okay, now the only thing that you have to do is to take this vector, or more exactly a matrix which can be seen as a vector, 593 by 1 tensor, and you have to multiply it with the tensor, with the x-test tensor, and then compute the results, and the results again compare it with the y-test in order to finalize the experiment. Okay. Okay, so what I'm going to do here, I'm gonna delete this one and ask just to show us the shape. Okay, and this is it. Finalize experiment with x-test dot tf dot tf theta vs tf y test. Okay, and just a short example before this, you can actually take the numpy of the theta directly, as well as the numpy of this dot product, in order to compare it with the numpy with the class, with the simple CPU representation, straight representation of this vector. You need to transform it into a numpy vector. So we just call a numpy and it will work. So it's type of numpy data, and then just a tf theta dot shape. Okay, so it's an ND array, numpy classical array, and the shape of the tensor is tensor shape 900 by 1. So this is it. Right now we're gonna skip straight to how we are using in simple and straightforward experiments TensorFlow, and we're gonna solve the problem we saw earlier. Alex is going to show you how you model in TensorFlow this problem of inferring car prices based on car properties, car features, car variables that you can fit in the model. And if we have time, we're gonna discuss a little bit about PyTorch, another framework, so we can see from at least 3 different perspectives the same problem. And finally, a short Q&A session. Alex, I'm going to stop the presentation and you can take it from here, okay?
Yes, thank you. So I'm sharing my screen now. Is everything okay? You should see.
No,
okay.
not yet.
Not yet?
No.
Now? It's okay?
It's good. Yeah, yes.
Yeah? Okay. So earlier, Mr. Damian presented you a way to find the weights necessary to model the function that can take the description of a specific car and present you the price, the estimated price for those specifications. In this section, we're going to dig a little a bit more into the TensorFlow framework, and we are going to present another way of training the model. We are actually going to use a deep learning model composed of a series of dense layers. And I'm going to present you the building blocks for creating your own neural networks. And you will going to see how the network is going to be trained in order to obtain at the end of the training the function that can approximate you the price for a specific set of car specification. So while Mr. Damian presented you earlier the previous sections, I prepared the data loading process to skip this part. I'm just going to make a little presentation, a short presentation for research. So we're going to import the data into a data frame. You're already used with the columns from the data frame. We're going to extract the model and not use it for this presentation. And we're also going to extract the price column and use it as a target for our model. Mr. Damian told you and presented you why we should use the dummy column. So I'm just going to skip the presentation and I'm going to prepare the sparse matrix. So we have 593 columns, just as we had previously. Just a quick look, and everything seems to be just as Mr. Damian presented earlier. We're going to extract all the values into X variable, and we're going to split the data set into two parts. A part that we are going to use for the training and the part that we are going to use for the testing. So splitting and printing out the shapes. And we see matching between the X-train features and Y-train targets. And also we see a matching between X-test features and Y-test targets. Okay, so let's start on building our first neural network using TensorFlow. I'm going to import TensorFlow. We're going to shortly verify the version of the TensorFlow is 2.1. And right now we are going to create the model for our problem. We'll start with a very basic model, and maybe if we have time, we can create a method or a function that can receive some parameters, and based on those parameters, we can extend the model to contain multiple layers or multiple types of operations. But
I'm
first
pretty
of
sure
all,
we will have this time during the actual courses. Right now, it's more than unlikely.
Okay, I was just hoping. So
You can say that it's possible, but not probable.
Okay. So when you're building a neural network in TensorFlow, you basically have the following steps. So you always start with an input. Okay. So how do you define an input? You define an input like that. And I'm going to present you right now the key concepts. So from TensorFlow, we are going to use Keras as a framework for deep learning. This Keras has a set of layers, and in this collection of layers, there is a specific class called input, and this class allows us to enter in the model. So how we are going to enter in the model? By specifying what shape our data set, our training data set has. And our training data set shape is 593 based on the features of the data set. And we are just naming this input as imp. Just to be easier to continue with coding, I'm going to store in TFX this input. After we have the input into the model, we are going to create a series of functions. Okay, so our data gets into a model, and there are multiple functions that we are going to apply to this data in order to obtain a linear or multi-dimensional separable bounding that will allow us to predict the price for the cars. Okay, so right now let's build the first function that we are going to apply to our input data set. For this process, we're going to use a dense layer that will going to connect all our inputs to a specific set of neurons. We are going to use we are going to name this function as dense1, and we are going to use the activation relu. And we're going to apply this function. So this is a function right here. We're going to apply it over our input. I'm going to leave a comment here to study about other kinds of activations or we are going to present other kinds of activation in our course like tanhash, etc. After that, we can continue and build other functions after this one. So we're going to add another layer. We're going to apply this new function, dense2, over the previous output. Let's build another function. Let's say that we have 64 neurons. We name it dense3. We also use activation relu. And at the end, let's say that we are going to use the last function that is going to connect our 64 features to predict the price for the car. And we are just going to name it readout, but without activation. Okay, so this function is going to be applied over TFX. And now we have the data. So we have the model. So the model parts are the input, corpus, if you like, and the output. Okay, so these are the three main parts of the model. But we only have the functions right here. We don't have created yet the model. So in order to do that, we are going to use tf keras models model of inputs, and we are going to specify the input, outputs, we're going to specify our TF out. We can now go over the summary of the model and print the summary. Okay, let's use it here. Let's compile the model. Basically, the compile method allows us to specify the training procedure. So we have our model, but our model needs to know the error function, the loss function. We're going to use my as our loss function, and we're going to use SGD as the optimizer, and this optimizer will apply the gradients with respect of the loss values with respect to the weights. Okay, and optionally we can use metrics MSE optionally, or other kind of metrics. Okay, so now we have the model, the complete model. And what are we going to do right now is to start the procedure of training. So we'll specify that our model needs to be trained on the X-train data, having as target Y-train data for a number of, let's say, 200 epochs. And after every epoch, we want to see how good our model is by validating the model on the test data. Okay, so that should be it. But another important thing is to specify the batch size that we're going to use. We want to use a batch size of 33 observations to feed our model. And I think we can start. Okay, let's see. So it's not layer, it's layers. The first mistake. Okay. So this right here is the summary that we've printed. Okay, and in this summary, we will see the layers, basically the functions that we are going to apply on our data. This basically contains all the weights that will be trained in the training process. And right here, you can see the training process. But we have a little problem with our loss. I guess something is weird because our loss is none. And I think we have some problems. Okay, just a second.
Probably in the data, Alex, could be a problem in the, how many observations do you have?
So Xtrain has...
Is the classic one, 90,000, okay?
Yes, yes.
Okay, and the validation loss as well as the loss is none, right?
Yes, yes, both are none.
And in it's mean absolute error, and you are not activating anything at the end, right?
At the end, we don't have any activation, so
perfect. It's very
none.
straightforward. It's very simple, and it should work. There is a problem in the data probably. We have something that it's not very nice there. Have to see exactly what it is. I don't think we have time for that, but what you have to understand and what is very important in this experiment and in this process and in these classes is you have to understand that we will show you and we are showing you the thought process, the whole engineering process and the research process. So it's not scripted. It's not something that probably rehearsed before in the mirror, because this is the right way to do data science. And this is the right way to experiment, and this is the right way to understand, and this is the right way to consolidate your knowledge. No matter if you have seen before data science, if you worked before with deep learning frameworks, with TensorFlow, and you did some few models, or maybe you even did artificial intelligence masters in computer science university. You have a lot. You still have a lot to learn, and the whole purpose of these courses is to plug you inside the science of data, basically in data science with deep learning. So okay,
just want to try something.
Okay.
Maybe it's from the missing scaling. I see that odometer has very large values.
Okay.
Maybe. Okay. So now xtrain, xtest, ytrain, mytest.
Just for the fit, it's enough. Okay, that's the last, and it's still going, it's going, and it's gone. Okay, it's good.
Okay, yeah. So
okay, so basically, what actually did happen there? There was another way to demonstrate that was a problem. So basically, we could just decrease the capacity of the model, let's say from 256 to 10, or to 20 hidden units for the first layer and even smaller for the second. That way, the actual multiplication between all those big values and the weights would have been much lower. What we had in this case, we had a classic case of number overflow. So basically, the number was too big to be kept inside the CPU, and it wasn't considered a real number. It was considered infinite. So when the loss was computed, the loss based on infinite, basically mean of the infinite is not a number, right? Another option would have been to leave the data unscaled and leave the network as it is and drastically decrease the batch size, let's say to 3 or 4 observations. And that again would have allowed us to have smaller values in the matrix multiplications. But of course, all those ideas that I told you are just intuitive directions that you go to explain what is going on. However, the right way to do it is to scale the features, of course, so that you don't have these unbalanced values between different variables and they do not generate numbers that are considered infinite or minus infinite, or let's say in the best case, the model is going to focus only on those numbers and not at all, and zero focus on the small numbers that are considered unimportant versus these very big large numbers. Okay, so Alex,
yeah, our training will take some time. I mean,
will take some time. I think we're gonna switch and show the same thing to, you can leave it just a second. Let me start another notebook, and we can see how the same thing you did looks like in another framework in PyTorch. So we're gonna in order to complete our journey in the courses and in the world of deep learning frameworks and machine learning in general.
Is it okay to stop sharing right now?
Just a second.
Okay,
Just
okay, no
let
problem.
me. Okay, I think it's okay right now.
Okay. Thank you.
Okay, thank you. Okay, and I'm gonna share my screen again. And this is the sharing. Okay. Can you see it? Not yet, I think. Maybe, not sure.
Not yet. Yes, it's okay.
Is it showing?
Yes, yes.
Perfect. Okay, so we're gonna import PyTorch and we're gonna see the version. I have 1.4 on this computer. It's actually, I think, 2 or 3 releases old. Okay, straightforward, we're gonna copy paste from the previous project the loading of the data. So we had the import pandas and we have the loading of the data from the car sample data set, the reading, the popping of the model, which is a little bit much. Now in deep learning, we shouldn't do this. We don't need to do this. However, we are doing for the moment. And another thing that we are doing very badly here is that we shouldn't get the dummies of the data. We should use another technique, such as those techniques that are really making difference in deep learning versus shallow learning, which is representational learning. And representational learning helps us construct specific representations for those features without sparsing them and without binarizing them and so on. Okay, so we have the data, and again we slice the data in this very bad way. Okay, and now we're gonna construct the model. So you've seen in the fast way of TensorFlow how you construct a model. Actually, in TensorFlow there is another model. There is another way, the one that is based strictly on tensor and tensor operations, which is very, very complicated, and nobody actually used it. It was used, I think, I'm pretty sure. It was used back in 2016, and in 2018 already Keras was adopted as a specific sublibrary of the TensorFlow, and nobody uses anything else in TensorFlow than Keras. With 2 different flavors, the object flavor and the functional flavor. Now in PyTorch is more like oriented towards science community, academic community, and it requires you to describe very nicely what you want to achieve. So basically, in order to write the model that Alex wrote, we have to write a class. By the way, there is another framework that appeared recently on the market. I think it's called PyTorch Lighting, and PyTorch Lighting is basically a Keras for PyTorch, which I totally dislike, because the whole point of PyTorch is to allow you to fine-tune your experiments and to go deep inside the problems that we are trying to solve. Deep and both explainable, but in the same time, easy to understand. So let's say class is a simple neural network. Okay, and it's inherited from torch.nn.module. All the neural networks have to be inherited from this one. And we define the constructor. It's classical object-oriented programming in PyTorch, of course. And we have as parameters the inputs. How many inputs we have, Alex? I think it's 593, right?
Yes, yes.
Okay, and a number of hiddens. We're gonna make just one hidden layer. And you know what? We're gonna make as many hidden layers as you did in TensorFlow. How many hidden layers?
Three were.
Oh, so it's the first one and the second one and the third one and then the output, or
yes.
4 hidden layers. Oh, okay, or let's say 3 hidden layers better.
Yeah.
Hidden hash1 equals how many?
256.
Okay, and hash h2 equals 128, and number of hidden units for h3 it's 64. Maybe?
Yes.
Okay, and this is it. And now this is mandatory, so everything should be initialized by the PyTorch framework. So now we define the layers as properties of this class we are writing. So it's layer 1 equals with torch.nn.linear. So basically it's a linear operation, just a method of multiplication, similar with dense in the TensorFlow framework. The inputs are n inputs and the outputs it's n hash 1. So you have to say how many inbound connections are within this operation and this node of the graph, and how many outbound are out of this graph. It's the first time I used the word graph in our webinar, and I think it's very important because everything you see here, anything we do in deep learning, it's basically a directed acyclical graph. Okay, so after this operation, you have to do some kind of activation. And Alex, you used what activation?
Relu.
Relu. So it's a linear. It's a very cool name for a very simple operation, which is rectified linear operation unit. Rectified linear unit, yes, which is nothing else than 0 if the value is below 0, and the value if the value is above 0. So it's something like a max between 0 and x. That's it. That is f of x. Sorry for the small Romanian inserts in my language. F of x equals to max of 0, comma x. So if the value of x is below 0, it will be 0. If the value is above 0, it will be x. Excellent. The only problem of this function is that it's not differentiable in point 0. So the next one, layer 2, it's, let's make a small trick. And so it entered the inbound connections are from the previous layer. The outbound are for the next one. Okay, let's do it again. The trick. Be very careful with copy paste. Sometimes it's not that great. Okay, and we have the third layer. Alex was very picky with his architecture, obviously. Okay, and we have H2 and outbound H3 and the activation. And finally, thank you, Alex, we have the readout layer, which is actually a linear unit that has an entry of NH3 units and an output of 1. Is just a matrix multiplication, nothing else. I always like to do like this, returns. Maybe it's from my past C++ background. Forward. Okay. So in the second, after we define the layers inside the PyTorch class, inside the PyTorch graph, we have to define the way the data should be processed. So based on this, the system doesn't know anything. The framework doesn't know what to do with your data. So we have to define the way forward, let me emphasize it, in the graph. That's all. So we have inputs, let's say inputs, sorry. And those inputs first have to be passed through self.layer1. Of course, the inputs must be of this dimensionality, otherwise it will give an error. Okay, so self.activation1 of DAX. And now we're gonna do the previous trick. The second layer, the third layer. Sorry. I don't do a lot of copy paste, so sometimes it doesn't work the way I want. Okay, so we pass through the first layer, we activate the linearities, then we pass through the second layer. Okay, we activate again those linearities, and we could have used the same function act1, but I'm going to show you why. Okay, and then layer 3, and then layer 3, and now we have to put here the right input, and then return self.layer, readout, right, of THX, and this is it. That's the whole definition of the network. Now we can say, sorry, I think it's okay. Now we run it and say model equals simple and n of, we leave it like this because we already defined the inputs as we wanted. And now we just print the model. Okay, so you see the actual structure. So we have an input layer, layer 1, with 593 features, and then we multiply it with a weight matrix of 500 by 256, and we obtain 256 activations, and then we, not activation, linearities, I apologize, and then we activate those linearities with the relu activation function. Then we paste 2 times more, thanks to Alex, through 2 different layers, and then finally we compute the output with just a simple matrix multiplication and linearity. Now, due to the lack of time, I'm gonna just write what would be the next steps. So we have the data in the simple format, we have the definition of the layer. The following step would be to create a data set, torch data set, that we can iterate into with the training loop. Something that was done very simply in the TensorFlow Keras variant, and everything was done behind the scene. We didn't have to do anything. Okay. And now the final one is iterate through batch of records, observations, records, and optimize using back propagation. Okay, and this is also a markdown, and of course that should be here. And basically what this means, this is a whole research topic, and maybe even more than one research topic. And we will dedicate a lot of time in our courses in this particular area of understanding how backpropagation works, how we can babysit the optimization process. And you see, you've already seen, and it wasn't scripted. We didn't talk, okay, let's put some kind of error so the optimization doesn't work, so we debug it, we solve it, and we go forward. That is the kind of problems, of optimization problems, that in TensorFlow it's a little bit more complicated to do than in PyTorch, because here you have more control. You see everything that is under the hood. There is no simple way of doing please take care of this. No, you have to do it manually. You have to iterate through all the batches and finalize the optimization process with a clear algorithm, not something that just happens behind the scenes. Of course, also in TensorFlow you can do that, but and we generally do that everybody does that. Nobody uses simple fits, you know, like you've seen there. Only when you have simple experiments and you have to iterate rapidly models, and you have to understand how the model behaves versus a particular sample of data. So this is it. I think we have just a few minutes left for Q&A, and I'm more than happy to answer any questions you might have. I think we bombarded you with a lot of information, from data sets to simple models to tensorial computation to TensorFlow model creation and simple Keras-based optimization, PyTorch, how it relates to data science versus TensorFlow. A lot of information, I know, but you know, this is just a preview.
Okay, thank you.
Thank you, and goodbye.